Every single time you use your phone or your computer or even start your car, you're depending on something so small and so numerous, it's pretty much invisible. It is the true unsung hero of our modern age, the absolute building block of our entire digital world. Today, we're talking about the transistor. Okay, just look at this number. 50 billion. And no, that's not some crazy prediction for the future. That's about how many transistors can be packed onto a single, high-end computer chip right now. We're talking about a little piece of silicon that's smaller than a postage stamp. The scale is just, well, it's completely mind-blowing. All right, so we get it. There are a ton of them, and they're incredibly important. But that brings us to the real question, right? We hear the word transistor all the time, but what is this microscopic marvel of engineering actually doing inside all our gadgets? How does it even work?
Well, you might think it's some super complex thing, but really, when you boil it all down, a single transistor has two basic jobs. It can be a switch, or it can be an amplifier. And those two simple functions, well, they make everything else possible.
So let's break that down. As a switch, it's literally just controlling the flow of electricity. It can stop it or it can let it go. It's either on or off. And that simple idea creates the ones and zeros, the binary code that is the language of all computers. Then, as an amplifier, it does something else amazing. It takes a tiny, weak electrical signal and cranks it up, making it way stronger. That's absolutely vital for stuff like hearing aids or radio transmitters.
Let's just focus on that switch function for a second. That simple on or off. That is the fundamental atom of our entire digital universe. Seriously, every picture you look at, every app you open, every piece of information stored anywhere, it all comes down to a massive collection of these tiny switches flipping on and off at unbelievable speeds.
And the amplifier side is just as important. Think about it. The radio signal that your car antenna picks up is incredibly faint. There's no way it could power your speakers. That's where the transistor comes in. It grabs that weak signal, gives it a huge boost, and turns it into the music you actually hear. That's what we call current gain, making something small, powerful.
So the big question is, how can one little device do both of these critical jobs? The secret isn't some tiny, complicated machine with moving parts. Nope. The answer lies in the almost magical properties of the material it's made from. Silicon. Yeah, basically the same stuff that makes up sand.
You see, silicon is a very special material called a semiconductor. That means it's not a great conductor like copper, but it's not a great insulator like rubber either. It lives in this perfect middle ground. And the best part? We can control how well it conducts electricity. That control, that's the whole secret right there.
So how do we control it? Through this really fascinating process called doping. Now, it's not what you think. It's all about adding tiny, precisely measured amounts of other elements, impurities, into the super pure silicon. And doing that completely changes how electricity moves through it.
Okay, so here's how that works. You start with pure silicon. Now, if you dope it with something like phosphorus, you end up with extra electrons just hanging around, ready to move. We call that N-type silicon for negative charge. But if you use an element like boron instead, you create these little holes where electrons should be but aren't, and that creates P-type silicon for positive charge.
All right, so now we've got our two key ingredients, N-type silicon and P-type silicon. The next step is to actually build the transistor, and the most common way to do it is to layer them together, kind of like a tiny high-tech sandwich.
And this is basically what it looks like. It's called an NPN transistor, and you can probably guess why. It's a thin slice of that P-type silicon stuck right between two layers of N-type silicon. That's it. Structurally, it's that simple. Now, each of these three layers has a name and a job. The first N layer is the collector, and it's basically a big reservoir of electrons. That super thin P layer in the middle, that's the base, and it's our control handle. And finally, the other N layer is the emitter. That's where the electrons are going to exit the device.
So we've got this NPN sandwich, but how does that structure actually let us control the flow of electricity? Well, to make this super clear, we're going to use a really simple analogy that I think you'll find pretty perfect. A regular old water tap. Okay, so just picture it. The main water pipe coming into your house, the one with a huge supply of water, that's our collector. The little handle you turn to get the water flowing, that's the base. And the faucet itself, where the water pours out, that's our emitter.
See how this works? It takes just a tiny little bit of effort to turn the handle. That's like applying a tiny electrical current to the base. But that small action unleashes a massive flow of water from the pipe to the faucet. In our transistor, that tiny current at the base allows a huge flow of electrons from the collector to the emitter. Turn off that small current at the base, and the whole flow just stops. It's a switch and an amplifier all in one beautiful, elegant action.
So, we've seen how one single transistor works. It's this incredibly clever little electrical date. But the real magic, the revolution, happens when you figure out how to put not one, not 1,000, but billions of them together on a single chip.
This quote just nails it, doesn't it? That one simple principle, a small current controlling a much larger one, is the engine that drives our entire digital world. I mean it. Every single computer, phone, and TV you've ever used runs on that exact foundation, just repeated billions and billions of times over.
And the speed at which we've scaled this up is just wild. Back in 1971, the first ever microprocessor, the Intel 4004, had about 2,300 transistors. Fast forward to 1993, the Pentium processor had over 3 million. And today, like we said at the start, we've blown way past 50 billion. That exponential growth is what's known as Moore's Law.
So there you have it. We've gone from a simple piece of treated sand to a global civilization that runs on these tiny little gates. A single transistor is really just a simple switch, but when you put billions of them together, they create our digital world, the internet, AI, everything. It really makes you stop and think, right? As we're now figuring out how to pack not just billions, but maybe trillions of them onto a single device, what new world will they help us build next?